A comment I made in a LinkedIn group discussion prompted a request for further information and documentation. A complete response to that request involves literature going back 40 years, plus a need to analyze ramifications of changes in inertial navigation since then. The changeover from gimbaled platforms, commonly used in the early 1970s, to strap-down today is pivotal. One way to explain all that is to start with a very old reference. It's 40 years old, but it contains information remaining important to this day. It was written by one of the top aerospace experts of all time. Here I cite two references from Professor A.E. Bryson. He gave me draft copies while I was preparing my 1976 book, which he reviewed as noted in its acknowledgments. Neither the first one, an internal Stanford report, nor the second, a contract report, was as readily available as many other writings. While my 1976 book cited both, word processing wasn't yet commonplace, so there's no file for either one of them. When this topic recently came up, I talked to him by phone for the first time in over a year. He agreed that I could paraphrase that work and summarize what it means to our industry today. The first document starts with the familiar dynamic equations in a geographic reference frame expressing relationships between errors in horizontal velocity and in apparent directions of the navigation reference frame, with the role played by biases in gyros and accelerometers. In this study, the IMU is stationary, so the first thing to look for is any ramping in horizontal velocity. That will happen when the 1g upward restoring force has a non-zero projection along a direction that was thought to be horizontal. Suppose either your apparent north or east velocity is not only off zero, but it's changing by almost a centimeter per second, more like 0.98 centimeter per second every second. Then you might conclude that either the accelerometer is tilted by a milliradian, as depicted in this sketch, or instead you might believe a milli-g bias caused the velocity ramp. Or maybe it's tilted by a half milliradian and it has a half milli-g bias. Or maybe it's tilted by 2 milliradians with a milli-g bias in the other direction. Or maybe 100 other possibilities giving that same net effect. Observed velocity history doesn't enable us to distinguish between accelerometer bias and tilt angle effects at rest. This explains why a very early step in this investigation was to define the choice of states. Bryson immediately combined certain ones in order to gain observability by reducing state dimensionality. The first combining choice involved leveling errors and accelerometer biases. The reason for this is clearly observability. False ramping of velocity is the combined effect of a tilt and an accelerometer bias. The ramp slope in each level axis is an algebraic sum of two unknowns. At first, then, you can't separate them during initialization. Now it's time to consider what happens next. If you're unable to tell them apart initially, then it seems logical to conclude that you still can't separate them a second later. What about a minute later or 10 minutes later? The key to the answer is, as it always has been, in the propagation dynamics. We all understand that tilt plants a seed for velocity error by interacting with the full amount of specific force, which, after leveling at rest, is no longer constrained to stay at 1g. The time history of dynamics experience, then, will characterize the behavior of the effect on velocity error. The other influence being investigated, accelerometer bias, has a different propagation pattern. It's very common to see that pattern characterized with exponential decay. Ironically, that was much more realistic 40 years ago than it is today. When most inertial navigation systems were mechanized with a gimbaled platform, the instruments experienced very little rotation. Today they're subjected to the full angular rates of the vehicle because of strap-down. The implications are profound. For a tip of the iceberg indication, see the URL on gyro mounting misalignment cited here. And then throw in another whole set of additional error-generating sources due to vibrations. Although the vibrational waveforms tend toward zero average, they produce biases through rectification. For explanation, if your library has a copy of my 1976 book, see Chapter 4, or my 2007 book, see Addendum 4B. Modeling inertial instrument errors as band-limited random noise has severe limitations in the presence of dynamics. Even if the paths are straight, the vibration modes can change, at least in spatial orientation, as the plane flies through changing wind direction, or a ship advances through changing water currents, or a land vehicle moves over bumpy roads. In order to use the noise through a low-pass filter model for gyros or accelerometers, then, at least one of the following design steps will be necessary. You could insert a full online compensation for all motion-sensitive degradations ahead of the estimation algorithm, or you could limit the effective data averaging duration of the estimation algorithm to a very brief period, and/or, instead of carrying separate states for accelerometer biases, use Bryson's revised misorientation states throughout. These are now discussed in sequence. The first of these steps would be premature at this time. Although an online compensation effort is being pursued, validation in flight will be necessary. Simulation cannot be relied on because of its widely recognized intrinsic limitation. Simulated input data missing real-world error characteristics can lead to a false sense of security. Real-world gyro and accelerometer errors defy exact characterization. The second step is an automatic result of using high levels of process noise in the estimation algorithm. The relation between the effective data averaging duration and the process noise spectral densities is shown in the books cited earlier, specifically Equation 557 of the 1976 book and Section 4.5 of the 2007 book. For the flight results in Chapter 8 of the latter, I set those averaging durations to values on the order of 15 seconds for gyro drifts. That was enough to enable centimeter per second RMS horizontal velocity accuracy. See the table at the bottom of this URL. The third step, combining off-vertical tilt and accelerometer bias effects into one state for each horizontal channel, is something I've always done ever since I saw Bryson's paper. Moreover, I'll continue to do that indefinitely until the online calibration effort mentioned earlier is an accomplished fact. I realize that's going against the usual custom, but remember its origin, and it is validated by flight results. Feeding the same flight data to a modified Coleman filter with accelerometer bias states included separately produced no benefit at all. They just aren't observable separate from leveling error. The only accelerometer bias state used was along yaw. It deviated from vertical during turns, but vertical dynamics didn't exhibit any more disturbances beyond bumps and wiggles normal in flight. And carrier phase residuals plotted in that Chapter 8 were well behaved throughout. To other GPS-INS algorithm designers, I recommend adopting Bryson's combined state for another reason: risk of computational instability. For that issue, I took a cue from other manuscripts co-authored by, you guessed it, Bryson. In a subsection entitled Minimum State Selection, on page 177 of my 1976 book, I showed how unnecessary augmenting and/or unnecessarily high order can allow large errors among estimated states to counterbalance each other, producing a trivial reduction in the scalar being minimized. Since that minimization is the criterion for optimization, those large but opposing states would be christened as optimal. A more detailed discourse on that subject appears in the group discussion from LinkedIn mentioned earlier. In the recent phone conversation with Bryson, he reiterated, effects that cannot be separated should not give rise to separate states. For stability, use one state covering their combined effect. His revised tilt states adjusted for accelerometer bias effects become observable within less than a minute. Other variables involved in the initialization took longer. Azimuth direction error and north gyro drift, both of which were redefined for combination with errors in the east channel, became observable within about 10 minutes at rest, and it was shown that azimuth gyro drift would require almost 4 hours to become observable. That motivated a desire for turns or speed changes to correct azimuth direction in flight, the subject of the second reference cited at the start of this presentation. That topic is widely recognized now after 40 years. Immediately, I'll mention here, when we apply that prescription today, we need to be conscious of those motion-sensitive gyro and accelerometer degradations. Again, the gimbaled platforms of the 1970s allowed exponential decay for characterizing biases. Very long time constants, if not ruled out by cost considerations, were not dismissed. Today's error models are complicated by a host of other sources. In summary, awareness is important in adapting design concepts to current times. Some principles remain. Bryson's revised state adjusting leveling error for accelerometer bias is still needed to this day. Other practices from decades past need to be revised. You won't see undistorted Schuler cycles in the presence of path changes with motion-sensitive degradations of strap-down inertial instruments, nor with updating applied to tilt or velocity components.